What if I told you that the very foundation of our universe isn't just empty space but a seething, bubbling ocean of invisible energy, a place where particles flicker in and out of existence in the blink of an eye, and the laws of physics as we know them seem to bend and twist? This isn't science fiction. This is the quantum vacuum, the hidden stage upon which the entire cosmos performs. It's been called the fabric of reality itself, a paradoxical void that's anything but empty. In fact, it's alive with unimaginable potential, brimming with mysteries that challenge everything we think we know about the nature of existence. For centuries, we've gazed at the stars, wondering about the vastness of space. But what if the deepest secrets of the universe aren't just out there? They're right here, woven into the fabric of the so-called nothingness all around us. The quantum vacuum defies common sense. It's a realm where energy arises from nowhere, where ghostly particles dance at the edge of perception, and where the very concepts of something and nothing blur into uncertainty. Scientists have spent decades peeling back its layers, only to uncover more questions than answers. And that's where things get truly fascinating. In this journey, we'll explore 30 of the most mind-bending mysteries hidden within the quantum vacuum phenomena, so strange they seem ripped from the pages of a cosmic thriller. From the unsettling Casimir effect, where invisible forces push and pull at nothingness, to the startling possibility that the vacuum itself might hold the key to unlimited energy. Each revelation pulls us deeper into a world where reality is far wilder than we ever imagined. So buckle up. By the time we're done, you'll never look at empty space the same way again. Even in the deepest, most perfect vacuum where classical physics tells us nothing should exist, reality has a different story to tell. The quantum vacuum is anything but empty. It crackles with an infinite sea of energy, a phenomenon scientists call zero-point energy. Picture a calm lake at night. On the surface, everything seems still, but beneath, tiny ripples flicker endlessly. That's the quantum vacuum, a restless ocean of particles and antiparticles popping into existence for fleeting moments before vanishing again. This isn't just theoretical. Experiments like the Casimir effect prove it. Place two uncharged metal plates incredibly close together in a vacuum, and an invisible force pushes them together. Why? Because the vacuum itself exerts pressure, squeezing out some of those quantum fluctuations. But here's the real puzzle. If this energy is infinite, why can't we tap into it? The math breaks down, leading to what physicists call the renormalization problem. When you calculate the energy, the numbers spiral into impossibly large values, infinity, in fact. Scientists have clever tricks to sidestep this, but the deeper mystery remains. What if we could harness even a fraction of this boundless energy? Some speculate it could revolutionize technology, powering everything from starships to cities. Yet for now, zero-point energy remains locked away in the quantum realm, taunting us with its untapped potential while defying our best attempts to understand it fully. If you thought zero-point energy was strange, wait until you meet its fleeting inhabitants, virtual particles. These aren't your ordinary subatomic building blocks. They're ghostly apparitions of matter and antimatter, blinking into existence for unimaginably short bursts before vanishing back into the void. Picture spacetime as a frothing sea, where tiny bubbles of energy constantly erupt, particle-antiparticle pairs emerging from nowhere, only to annihilate each other in a cosmic heartbeat. This isn't just theoretical speculation. The math of quantum field theory demands it. Even in perfect emptiness, the universe refuses to sit still. But why call them virtual? Unlike stable particles we can detect, these are more like shadows, fleeting disturbances in the quantum field, never lasting long enough to be directly observed. Yet their effects are undeniable. Take Hawking radiation, the eerie glow predicted to seep from black holes. Here's how it works. Just outside a black hole's event horizon, virtual pairs pop up as usual. But if one particle gets swallowed by the black hole's gravity while its partner escapes, the escaped particle becomes real, stealing a tiny bit of the black hole's energy in the process. Over eons, this slow leak could cause even the mightiest black hole to evaporate. Now imagine zooming in on spacetime itself. At scales a billion trillion times smaller than an atom, the vacuum isn't smooth, it's a chaotic foam with virtual particles warping the fabric of reality into fleeting tunnels and bridges. Some theories suggest these microscopic wormholes might even explain quantum entanglement, linking particles instantaneously across vast distances. The implications are staggering. What if every empty corner of the universe is secretly teeming with this unseen activity, a hidden dance that shapes everything from black holes to the very structure of reality? One thing's certain, in the quantum vacuum, nothing is ever truly at rest. Einstein called it his greatest mistake, a fudge factor scribbled into the equations of general relativity to keep the universe static. He named it the cosmological constant, a mysterious energy woven into the fabric of space itself. But decades later, scientists made a jaw-dropping discovery. The universe isn't just expanding, it's accelerating. And that cosmic speed-up, it perfectly matched Einstein's so-called blunder. The twist, the energy driving this expansion, dark energy, behaves exactly like his discarded constant. But here's where the quantum vacuum throws a wrench into everything. According to quantum field theory, the vacuum should be bursting with energy enough to curve spacetime so violently that galaxies couldn't form, let alone life. The math predicts a vacuum energy density a staggering 10 to the power of 120 times larger than what we observe. That's a 1 followed by 120 zeros. Wrap your head around this. If vacuum energy were a swimming pool, theory says it should be an ocean drowning the universe. Instead, we're sipping from a teaspoon. Why the mismatch? Nobody knows. It's the widest gap between prediction and observation in all of physics. Enter dark energy, the faint whisper of pressure-accelerating cosmic expansion. It accounts for 68% of the universe's energy budget, yet its density is almost negligible compared to quantum predictions. Some theorists suggest an unfathomable fine-tuning. For our universe to exist, the colossal vacuum energy and the cosmological constant had to cancel each other out to within a hair's breadth. Others propose wilder ideas like hidden symmetries or undiscovered fields dampening the vacuum's roar into today's faint hum. One thing's clear, the cosmological constant problem isn't just a number puzzle. It's a screaming clue that our understanding of gravity and quantum fields is incomplete. Maybe the vacuum hides dimensions we can't see. Maybe empty space isn't fundamental but emerges from deeper physics. Whatever the answer, this glaring discrepancy between quantum theory and cosmology might just be the trailhead to a revolution in physics, one that redefines reality itself. Imagine the universe as a vast, tranquil valley, peaceful, stable, seemingly eternal. But beneath its calm surface lies a spine-chilling secret. Our valley might rest on the slopes of a much deeper abyss, a lower energy state of reality just waiting to be triggered. This is the nightmare scenario physicists call vacuum decay, the ultimate cosmic reset button. Here's how it could happen. According to quantum field theory, the vacuum we inhabit isn't necessarily the most stable state possible. It's like balancing a pencil on its tip, technically stable for a moment, but one nudge away from collapse. Our universe might be in a false vacuum, a precarious high-energy state, while a true vacuum, a lower-energy, fundamentally different reality, lurks just beneath the surface. If a tiny patch of space somewhere in the cosmos slipped into this true vacuum, it would create a bubble of destruction. Not the fiery explosion of a supernova, but something far stranger, a wall of redefined physics expanding outward at the speed of light. Inside this bubble, the very rules of existence would change. The Higgs field, the invisible energy field that gives particles their mass, could shift, altering the behavior of atoms, forces, even time itself. Chemistry as we know it would cease to function. Stars, planets, life, everything would unravel in an instant, rewritten by new laws we can't predict. The terrifying part, we wouldn't see it coming. The bubble's edge would move faster than light, leaving no warning, no time to react. One moment, reality as we know it; the next, a universe we wouldn't recognize. So what could trigger such an event? A high-energy particle collision, a freak quantum fluctuation, or even the natural decay of the Higgs field over trillions of years? The scariest possibility, it might have already happened somewhere in the cosmos. A single bubble could be racing toward us right now, unstoppable and undetectable until it's too late. Yet there's a twist. The Higgs field appears just stable enough for now. Experiments at the Large Hadron Collider suggest we're not on the knife's edge of collapse, but the margin is slim enough to keep physicists awake at night. Some theories even propose that vacuum decay might be impossible, that the universe is safeguarded by hidden symmetries or undiscovered principles. But until we know for sure, one haunting question lingers. Is our reality sitting on a ticking time bomb, or are we nestled safely in the only possible version of existence? The answer might lie in the quantum vacuum's deepest shadows, waiting to be uncovered, or perhaps to rewrite everything without warning. Here's something that will bend your sense of reality even further. What if simply moving through empty space could create heat out of nowhere? This is the mind-bending prediction known as the unravel effect. Picture an astronaut floating in the vacuum of deep space, far from any stars. To them, the universe appears cold, silent, and utterly empty. But now, imagine their ship suddenly accelerates. In an instant, the astronaut's instruments would detect something impossible. A warm glow of particles appearing out of the void, as if space itself were heating up around them. No external source, no hidden energy, just motion transforming nothingness into a thermal bath of quantum particles. So how does this work? It all ties back to Einstein's relativity and the strange marriage of quantum mechanics with motion. According to the unravel effect, an accelerating observer doesn't perceive the vacuum as empty. Instead, they see a sea of particles with a temperature directly linked to their acceleration. The faster you accelerate, the hotter the vacuum appears. This isn't just a mathematical quirk, it's a fundamental feature of how quantum fields respond to motion. The vacuum, it turns out, isn't an absolute concept. What one observer sees as nothing, another might detect as a bustling crowd of particles, all because their perspectives are moving differently through spacetime. Now here's where it gets even weirder. This effect isn't just some abstract prediction, it shares a deep kinship with Hawking radiation. Just as a black hole's gravity tears virtual particles apart, creating real radiation, acceleration through the vacuum does something similar. In both cases, what looks like empty space to one observer is a particle-filled frenzy to another. But here's the million-dollar question: are these particles real or just an illusion of perspective? Some physicists argue they're as real as anything we can measure after all. An accelerating detector would register them. Others counter that since a non-accelerating observer sees nothing, the particles are more like a trick of the math, a mirage created by the observer's own motion. The debate cuts to the heart of quantum reality. If the unravel effect is real, it means the very concept of particles depends on how you're moving. There's no universal vacuum state, just a patchwork of perspectives, each with their own version of reality. It also hints at something profound about the nature of heat and information. The particles detected by an accelerating observer carry energy, which means the vacuum itself holds a hidden thermodynamic structure waiting to be unlocked by motion. Could we ever observe this effect directly? The catch is the staggering acceleration required. To detect even a faint unravel glow, you'd need to accelerate at quadrillions of times the force of Earth's gravity. far beyond anything our technology can achieve. But some experiments with ultra-fast lasers or charged particles in accelerators might one day glimpse hints of this quantum thermal mirage. Until then, the unravel effect remains a tantalizing clue that the vacuum isn't just a stage for the universe, it's an active participant, reshaping itself for every observer who dares to move through it differently. So next time you feel the push of acceleration, whether in a car, a plane, or even just leaning into a turn, remember, in the quantum vacuum, motion doesn't just change your speed. It might rewrite the very fabric of reality around you. Stare at the night sky long enough, and it's easy to think of space as a vast, disconnected expanse, each star, each galaxy isolated in the void. But down in the quantum vacuum, the universe plays a very different game. Here, particles separated by light years can dance in perfect, instantaneous sync, as if space and time don't exist. This bizarre phenomenon, dubbed spooky action at a distance by Einstein himself, lies at the heart of the EPR paradox, a puzzle so unsettling it threatened to unravel quantum mechanics in the 1930s. The story begins with Einstein, Podolsky, and Rosen's thought experiment. Imagine two particles born from the same quantum event, twins linked by an invisible thread. Measure one spin, and its sibling instantly assumes the opposite spin, no matter how far apart they are. To Einstein, this was proof quantum theory was incomplete. How could information travel faster than light? Surely, he argued, there must be hidden variables, secret rules governing the particles' behavior. But decades later, experiments proved the particles really were entangled, their fates intertwined across any distance without any hidden hand guiding them. Now, here's where the vacuum gets eerie. This entanglement isn't confined to particles we create in labs. The quantum vacuum itself is a seething web of entangled states, a cosmic tapestry where every fluctuation is secretly paired with another. Picture a calm lake's surface, toss a pebble in and ripples spread outward. But in the quantum world, those ripples are mirrored by unseen counterparts, perfectly correlated even if they're light years apart. This isn't just theoretical. Experiments with quantum teleportation rely on this very principle, using entangled vacuum states to beam information across labs without physical transfer. But the real shocker, this entanglement might be the glue holding spacetime itself together. The holographic principle suggests our three-dimensional reality could be a projection of information encoded on a distant, two-dimensional surface like a cosmic hologram. And vacuum entanglement could be the mechanism stitching it all together. If true, every empty region of space is a hidden network of quantum links, whispering instantaneously across the universe. Some physicists speculate this could explain gravity's weirdness, that what we perceive as the gentle pull of mass might actually be the collective hum of countless entangled vacuum states. Others wonder if black holes, those ultimate cosmic shredders, preserve information in their event horizons through a dense fog of vacuum entanglement. One thing's certain, the vacuum isn't just empty space. It's a living, breathing entity where every flicker of energy is bound to another in a ghostly embrace. And as we pull at these threads, we might just unravel the deepest secrets of reality itself. Sometimes the most profound truths hide in the tiniest discrepancies. Take the humble hydrogen atom, the simplest building block of the universe. For years, physicists believed they understood its energy levels perfectly until one stubborn anomaly refused to fit the equations. This slight wobble in atomic behavior, barely a whisper in the data, would revolutionize quantum physics and reveal the invisible hand of the vacuum itself at work. The mystery began with a pair of electron orbits in hydrogen called the 2s and 2p states. According to Paul Dirac's then accepted quantum theory, these orbits should have identical energy. But in 1947, Willis Lamb and his student Robert Rutherford spotted something odd. Using microwave technology developed during World War II, they measured the energy difference between these states with unprecedented precision. The result, a tiny but undeniable gap, just 4 parts in a million. This Lamb shift shouldn't exist under classical quantum rules, yet there it was, a faint fingerprint of something deeper at play. The culprit, the quantum vacuum's ceaseless turmoil. Imagine the electron orbiting hydrogen's nucleus. Even in perfect emptiness, virtual particles from the vacuum constantly flicker around it. These fleeting disturbances slightly jostle the electron, like a boat bobbing on a choppy sea of quantum foam. The effect is minuscule but measurable. The electron's path deviates just enough to tweak its energy levels. That's the Lamb shift, vacuum fluctuations literally nudging reality off its predicted course. What makes this discovery earth-shaking isn't just the shift itself, but what it confirmed. Lamb's experiment became a cornerstone test for quantum electrodynamics, or CED, the theory describing how light and matter interact. The math of QED predicted these vacuum effects with stunning accuracy, matching Lamb's measurements down to the decimal. Suddenly, the vacuum wasn't just empty space, it was an active participant in atomic behavior, its ghostly fluctuations leaving detectable traces in the fabric of matter. Recreating Lamb's precision today still boggles the mind. His team used heated tungsten filaments to excite hydrogen atoms, then measured microwave frequencies needed to flip their states, all without modern lasers or computers. The margin for error was vanishingly thin. Even thermal vibrations in their apparatus could have drowned out the signal. Yet they succeeded, proving nature favors the quantum vacuum's whispers over our classical expectations. The legacy of this tiny shift echoes through modern physics. It's why atomic clocks, which rely on hyper-precise energy transitions, must account for vacuum effects to avoid drifting by nanoseconds. It's part of why quantum computing demands such extreme isolation. Stray vacuum fluctuations can introduce errors in delicate qubit states. Even the search for new physics often starts here by measuring atomic behaviors with Lamb shift-level precision, hunting for discrepancies that might hint at undiscovered particles or forces. Perhaps most astonishing is how this all connects back to the vacuum's duality. It's both nothing and everything, a void that sculpts reality through its invisible turbulence. The next time you see a neon sign's glow or a laser's crisp beam, remember, their colors owe a subtle debt to the restless quantum sea beneath all things, forever shifting, always whispering. Imagine holding the pure essence of light in your hands, not just beams or photons, but raw electric fields so intense they tear reality apart. This is the realm of the Schwinger effect, where emptiness itself gives birth to matter under pressures beyond imagination. The concept seems ripped straight from mythology, summoned particles from nothingness, conjuring electrons and their antimatter twins, positrons, out of thin air. But this isn't magic, it's physics pushed to its extremes. At the heart of this phenomenon lies a simple yet staggering idea. If you crank up an electric field past a critical threshold, the quantum vacuum can't stay empty. Picture the vacuum as a taut fabric, stretched thinner and thinner until it snaps. When the field strength hits around 1.3 times 10 to the power of 18 volts per meter, a number so vast it dwarfs anything in our everyday experience, the field's energy becomes dense enough to spontaneously create particle-antiparticle pairs. Like cosmic alchemy, energy transforms directly into matter, borrowing from the field's fury to populate the void with tangible particles. Nature's most violent laboratories showcase this in action. Take pulsars spinning stellar corpses with magnetic fields a quadrillion times stronger than Earth's. Near their poles, electric fields grow so powerful they rip the vacuum apart, birthing cascades of electrons and positrons that light up the surrounding space like a celestial fireworks display. These particles get whipped into jets, radiating energy across the cosmos and painting the skies with their glow. On Earth, we're not quite at pulsar-level intensities yet. But lasers are bringing us closer. Modern ultra-high power systems, like the European Extreme Light Infrastructure, can concentrate beams to intensities where the Schwinger effect might finally be glimpsed in a lab. The trick lies in harnessing tightly focused pulses so brief they last mere femtosecond millionths of a billionth of a second. In those fleeting instants, the laser's electric field spikes enough to tease pairs from the void, offering physicists a miniature window into processes usually reserved for neutron stars. Why does this matter beyond the sheer wonder? Because the Schwinger effect blurs the line between energy and matter in ways that could rewrite fundamental physics. Some theories suggest similar mechanisms might explain how the early universe filled with particles after the Big Bang, a firestorm of pair production kickstarting cosmic complexity. Others speculate that mastering this effect could unlock new energy technologies, though the staggering field strength required make that a distant dream. For now, the Schwinger effect remains a testament to the vacuum's latent creativity. It's a reminder that what we call empty space is anything but passive. Given the right conditions, the void itself becomes a forge, and light, the hammer that shapes existence. Astrophysics has a dirty little secret when we peer out at the cosmos. The math just doesn't add up. Take galaxy rotation curves, for example. Stars on the outer edges of spiral galaxies whip around their centers so fast that, according to Newton's laws, they should fling themselves into the void. But they don't. Something invisible grips them, an unseen force we call dark matter. Yet here's where the quantum vacuum throws a curveball. What if the answer isn't just an unknown particle, but a ghostly interplay between dark matter and the vacuum's hidden energy fields? The discrepancy starts with gravity's stubborn refusal to behave. Einstein's general relativity works flawlessly for planets and stars, but at galactic scales it stumbles. To make the equations fit, physicists had to invent dark matter, an elusive substance outweighing normal matter 5-to-1. But after decades of searching, we've yet to directly catch this cosmic fugitive. Could vacuum energy be part of the puzzle? Quantum fields permeate every inch of space, and their energy should, in theory, curve spacetime. Yet when we calculate how much gravity the vacuum ought to produce, the numbers explode into nonsense. The predicted effect is 120 orders of magnitude too strong. If the vacuum's energy fully contributed to gravity, galaxies wouldn't just rotate weirdly, they'd never form at all. This glaring mismatch is the vacuum catastrophe, and it points to something profound. Either our understanding of quantum fields is fundamentally broken, or the vacuum's energy interacts with gravity in ways we can't yet fathom. Some theorists propose wild solutions. Maybe dark matter isn't a particle but a shadowy sector of vacuum fluctuations that only tug on spacetime in specific ways. Or perhaps the vacuum's energy isn't uniform. What if it clumps in invisible pockets, masquerading as dark matter's gravitational pull? There's tantalizing, if controversial, evidence. Certain modified gravity theories, like MUND, tweak Newton's laws to explain rotation curves without dark matter. But even these can't fully account for observations like the Bullet Cluster, where colliding galaxies seem to separate their visible matter from their gravitational bulk, as if something invisible is leading the charge. Then there's the Casimir effect's sneaky hint. Remember those metal plates that mysteriously attract in a vacuum? The same quantum pressure might operate cosmically. If vacuum fluctuations vary in strength, say, weaker in the void between galaxies and stronger within them, that gradient could mimic dark matter's gravitational fingerprints. No wonder some physicists are re-examining old assumptions. Maybe dark matter doesn't just sail through the vacuum unaffected. Maybe they're locked in a hidden dance, their interplay shaping the cosmos on scales we're only beginning to grasp. The deeper we dig, the clearer it becomes. The vacuum catastrophe isn't just an accounting error. It's a flashing signpost pointing toward a deeper layer of reality, where the quantum foam and the cosmic web are tangled together in ways we've barely begun to untangle. Until we solve this riddle, the universe's true ledger, Its balance of mass, energy, and gravity remains half-written, waiting for a key we might one day pluck from the vacuum's restless depths. Imagine being able to shake empty space hard enough to make light appear out of nowhere. No light bulbs, no stars, just pure motion transforming nothingness into glowing photons. This isn't a far-fetched thought experiment. It's the dynamical Casimir effect, one of the most mind-bending demonstrations that the quantum vacuum is anything but passive. While the classic Casimir effect shows how empty space can push objects together, this wild cousin proves that movement itself can rip particles from the void. The key lies in the vacuum's strange duality. Even in complete darkness, quantum fields hum with potential energy, filled with fleeting pairs of virtual particles. Normally, these pairs vanish almost instantly, but introduce rapid change, like a mirror moving at nearly light speed, and something extraordinary happens. The mirror's motion disturbs the quantum field so violently that some virtual particles can't annihilate back into nothingness. Instead, they're kicked into reality, becoming measurable photons. Think of it like dragging a paddle through still water. Suddenly, ripples emerge where there were none. Except here, the paddle is a mirror and the ripples are literal light. Now, vibrating a physical mirror fast enough to achieve this sounds impossible after all. Nothing solid can move at relativistic speeds without shattering. But in 2011, physicists at Chalmers University of Technology in Sweden pulled off the next best thing. They used a superconducting circuit engineered to act like an electromagnetic mirror. By flipping the circuit's magnetic field direction at a staggering speed billions of times per second, they effectively made the mirror vibrate at a fraction of light speed. The result, photons popped into existence exactly as quantum theory predicted. This experiment wasn't just a cool party trick. It confirmed that the vacuum isn't an empty stage, it's an active medium responsive to changes in its environment. The implications stretch far beyond the lab. Some astrophysicists speculate that extreme versions of this effect could occur in nature, like near rapidly vibrating neutron stars or collapsing black holes, where spacetime itself is warped at insane speeds. Could this explain mysterious cosmic light emissions we've yet to fully understand? And here's where it gets even stranger. The photons created via the dynamical Casimir effect aren't random. They emerge in entangled pairs, a quantum link forged from pure motion. This hints at a deeper truth. The vacuum might be a vast, unseen network of potential connections, waiting to be unlocked by the right kind of disturbance. Who knows what other particles, electrons, protons, even entire atoms might be coaxed out of the void with the right experimental ingenuity. For now, the dynamical Casimir effect remains a dazzling reminder that the universe loves a good loophole. Energy isn't just conserved, it's constantly shape-shifting, hiding in plain sight until motion or change gives it a nudge into reality. Next time you flip a light switch, consider this. Somewhere in the quantum shadows, an invisible mirror shaking at the edge of spacetime might be doing the exact same thing, summoning light from the nothingness itself. Take a perfectly symmetrical wine bottle, the kind with a deep, circular indentation at the base. Now, place a marble at its very center. In theory, the marble should stay perfectly balanced, honoring the bottle's symmetry. But one nudge, one tiny breath of disturbance, and the marble rolls off-center, landing in the indentation's rim. The symmetry is broken, not by force, but by the system's own instability. This elegant metaphor holds the key to one of quantum physics' most profound discoveries: how the vacuum itself shapes the mass of every particle in existence. The story begins with an unsettling puzzle. In the equations of the Standard Model, particles like electrons and quarks should be massless, zipping through the cosmos at light speed. But we know that's not true. Matter has weight, structure, solidity. The solution, a cosmic sleight of hand called the Higgs mechanism, where the quantum vacuum plays puppet master. Here's how it works. Just like our marble settling into the wine bottle's rim, the universe's fundamental fields can choose a preferred state, even if that state breaks their initial symmetry. Enter the Higgs field, an invisible energy field stretching through every inch of space, even in complete emptiness. Unlike electric or magnetic fields, which fluctuate in strength, the Higgs field has a constant, non-zero value in the vacuum. Picture this as the marble already resting in the bottle's rim before we even place it there. When other particles interact with this omnipresent field, they experience resistance, like wading through molasses, and this drag manifests as mass. The stronger the interaction, the heavier the particle. What's truly wild is that this symmetry breaking isn't just some abstract math trick. It's etched into the fabric of reality. Moments after the Big Bang, the universe was likely a place of perfect symmetry, where all forces behaved identically. But as space-time cooled, the Higgs field condensed into its current state, like steam settling into liquid water. That phase transition broke the symmetry, locking electromagnetism and the weak nuclear force into their distinct identities, and gifting particles with mass in the process. Without this vacuum-driven mechanism, atoms couldn't form, chemistry wouldn't exist, and the cosmos as we know it would be an unrecognizable blur of massless chaos. Now, here's where things get speculative and thrilling. If one symmetry-breaking event shaped our universe, could there be others? Grand unified theories predict that at energies 1 trillion times higher than what the Large Hadron Collider can reach, even electromagnetism and the strong nuclear force might merge into a single, symmetric force. Some models suggest the vacuum could harbor hidden layers of structure, waiting to reveal themselves under extreme conditions. Perhaps most tantalizing is the possibility that the Higgs field isn't in its lowest energy state, that our universe's vacuum is metastable, balanced precariously like a marble on a high shelf. A jolt of enough energy, and it might roll into a new configuration, rewriting physics in an instant. It's a humbling thought. The weights and measures of reality, from your body to the farthest star, owe their existence to the quiet, persistent bias of nothingness itself. So next time you pick up an object and feel its heft, remember, you're not just sensing matter, you're touching the fingerprint of a vacuum that refused to stay symmetrical. Back in the late 1920s, physicist Paul Dirac stared at his equations and saw something impossible, an infinite ocean of negative energy stretching beneath the fabric of reality itself. This was the birth of the Dirac Sea, a radical solution to a puzzle haunting quantum mechanics. You see, Dirac's own equation describing the electron worked beautifully, except for one glaring problem. It allowed for electrons with negative energy, a result that made no physical sense. Electrons losing energy should spiral down into these states, collapsing atoms and unraveling the universe. So Dirac proposed a wild fix. What if all those negative energy states were already filled? Picture the vacuum not as empty space, but as a vast, unseen, see every possible negative energy slot occupied by an electron, packed so densely they become invisible. Like water in a full glass, this sea wouldn't register in experiments, but pull an electron out, say, by adding enough energy, and you'd leave behind a hole. That hole, Dirac realized, would behave exactly like a particle with opposite charge, a positron, the electron's antimatter twin. His theory wasn't just mathematical sleight of hand. In 1932, Carl Anderson spotted positrons in cosmic rays, confirming Dirac's ocean was more than metaphor. Yet today, the Dirac Sea feels like a relic. Modern quantum field theory ditched the infinite ocean for a sleeker concept, the vacuum as a humming network of quantum fields. Instead of filled states, we now talk about fluctuations, particle-antiparticle pairs winking in and out of existence. The math works out the same, but the mental image shifts dramatically. No longer a stagnant sea, the vacuum becomes a dynamic stage where fields excite and quieten like waves on a restless shore. So why did physics abandon Dirac's vision? The sea model had baggage. An infinity of filled states meant infinite charge density, forcing awkward fixes. Quantum field theory streamlined this by reframing particles as excitations, sidestepping the need for a literal sea. But here's the twist: Dirac's intuition wasn't entirely wrong. The modern vacuum still retains echoes of his idea. Those fleeting particle pairs, they're the ghosts of his holes reshaped by deeper math, and in extreme environments like the intense fields near black holes, the distinction between sea and fluctuations starts to blur, revealing how closely the two pictures are related. Perhaps the most poetic legacy of the Dirac sea is how it reminds us that even discarded theories can hold truth. Dirac's infinite ocean was a stepping stone, a flawed but vital bridge between classical quantum mechanics and the richer tapestry of quantum fields. And though we no longer picture the vacuum as an electron-filled abyss, the spirit of his insight lives on in every positron, in every burst of gamma rays from colliding matter and antimatter, in the quiet hum of empty space that's never truly empty at all. Picture the early universe as a cooling pot of molten metal. As temperatures drop, cracks and imperfections form in its structure, freezing into place forever. The quantum vacuum might harbor similar cosmic scars, relics from when reality first transitioned into its current state. These aren't just hypothetical quirks. They're called topological defects, wrinkles in spacetime itself, and some theorists believe they could be lurking in the cosmos right now, warping space and time in unimaginable ways. The most intriguing of these defects, cosmic strings, filaments of pure energy thinner than a proton but stretching across galaxies, with the mass of entire mountain ranges compressed into every inch. Born from phase transitions in the infant universe, these strings would be under unimaginable tension, vibrating at near light speeds. When two strings cross or a loop snaps, the energy released could rival supernova, potentially explaining mysterious fast radio bursts, those powerful, millisecond-long blips of radio waves from distant space. Some models even suggest these strings might create double images of galaxies by bending light like a cosmic funhouse mirror, or leave telltale gaps in the cosmic microwave background. Then there are domain walls, sheet-like defects separating regions of space where quantum fields settled into different configurations during the universe's cooling. A single domain wall could slice through the cosmos like a knife, with matter on one side experiencing slightly different physics than the other. Fortunately, most theories predict these walls are rare. If they were abundant, their gravity would have torn the universe apart long ago. But what if microscopic versions exist? Some speculative ideas suggest they could be the source of dark energy, their repulsive gravity pushing the cosmos apart. The wildest possibility, these defects might not just be fossils. Certain grand unified theories predict networks of cosmic strings could still be forming today in hidden sectors of reality, shadowy realms of particles and forces interacting with ours only through gravity. If so, their vibrations might be generating faint gravitational waves right now, ripples we could detect with future observatories. Others wonder if primordial defects could seed bizarre objects like time-domain crystals, structures that repeat not in space, but in time, echoing the universe's first moments in an endless loop. Whether cosmic strings, domain walls, or something stranger, these vacuum scars remind us that emptiness isn't smooth. Like ice forming on a pond, the universe's cooling left fractures in the quantum fabric, and somewhere out there, those cracks might still be whispering. What if the vacuum isn't just a stage for particles and fields, but the most powerful quantum computer in existence, a cosmic processor encoding reality itself? This isn't just speculative fiction. Some of the boldest theories in physics suggest the quantum vacuum might operate like a holographic supercomputer, crunching the information of the universe in ways that make our most advanced machines look like abacuses. At the heart of this idea lies the holographic principle, a radical notion that all the information in a volume of space could be encoded on its boundary like a three-dimensional movie projected from a two-dimensional screen. Take black holes, those enigmatic cosmic shredders. According to the AD/CFT correspondence, a mathematical bridge between gravity and quantum theory, the information swallowed by a black hole isn't lost. Instead, it's smeared across the event horizon, the point of no return, like data etched onto a spherical hard drive. The vacuum surrounding the black hole might act as the medium translating that information, preserving it in scrambled form. Now stretch this idea to the entire universe. If the vacuum can holographically store and process information at black hole horizons, could it be doing the same everywhere, just on subtler scales? This gets even wilder when you consider black hole firewalls, the controversial idea that an invisible wall of searing radiation might lurk just inside event horizons. Where would the energy for such a firewall come from? Perhaps from the vacuum itself, its quantum fluctuations amplifying into a defensive barrier as information tries to escape. If true, the vacuum isn't passive. It's an active participant in enforcing cosmic rules, like a referee stepping in to prevent information loss, but the real mind bender. Spacetime itself might emerge from this vacuum-level computation. Think of reality as a pixelated image. Up close, you see individual dots, but step back and they blend into a smooth picture. Some physicists argue that what we perceive as smooth, continuous spacetime could be the macroscopic illusion of countless quantum bits in the vacuum, processing relationships between events. This isn't just philosophy. Certain quantum gravity models describe spacetime as a network of entangled connections, with the vacuum acting as the substrate that weaves them together. Imagine the vacuum as a cosmic loom, threading every particle interaction, every gravitational tug into a seamless fabric. When two electrons repel, it's not magic. It's the vacuum mediating their exchange of virtual photons. When a star bends light, it's not just warped space. It's the vacuum's underlying information geometry shifting to accommodate the mass. The implications are staggering. If spacetime emerges from vacuum-level computations, then black holes, wormholes, even the Big Bang might just be different programs running on the same quantum hardware. Could we ever test this? Faint hints might lie in the noise of gravitational wave detectors or the patterns of cosmic microwave background radiation, subtle glitches that reveal the pixelation of reality. Others suggest that tabletop experiments with ultra-cold quantum systems could simulate holographic vacuum behavior, offering a toy model of how information might manifest as space and time. One thing's clear: if the vacuum truly is a quantum computer, then we're not just living in the universe, we're living inside its processor, watching the output on the screen of our perception. And somewhere in the hum of empty space, the universe might just be running the numbers on what happens next. The idea of wormholes, tunnels through space-time connecting distant points in the universe, has long been the stuff of science fiction. But buried in the equations of general relativity, they're mathematically possible. There's just one catch: keeping a wormhole stable enough to traverse requires something stranger than fiction. It demands negative energy, a repulsive force counteracting gravity's crush, something the quantum vacuum might just provide. Picture a wormhole like a cosmic hallway with a habit of collapsing. Gravity wants to slam the doors shut the instant they open. To prop them open, you'd need a material that warps spacetime in the opposite way, something with negative energy density. In the 1990s, physicist Miguel Alcubierre proposed a similar concept for warp drives, using negative energy to contract space in front of a ship while expanding it behind. The fuel for such an engine: exotic matter, a substance with properties defying everyday physics. This is where the quantum vacuum's darker side enters. Under certain conditions, vacuum fluctuations can exhibit negative energy densities. The Casimir effect hints at this. When two plates suppress vacuum fluctuations between them, the region outside has comparatively higher energy, creating a pressure difference that looks like negative energy at work. Could this phenomenon, scaled up, stabilize a wormhole? The math suggests it's theoretically possible, but the numbers are daunting. You'd need a galaxy's worth of negative energy packed into a microscopic throat just to keep a centimeter-wide wormhole from imploding. Yet quantum mechanics might offer loopholes. Some theories suggest that if wormholes exist at subatomic scales where quantum foam churns with tiny tunnels, they could be held open by vacuum energy's negative fluctuations. These wouldn't be traversable by humans, of course, but they might allow information to pass, raising wild possibilities for quantum communication. Others speculate that higher dimensional physics or undiscovered quantum fields could amplify vacuum effects, making macroscopic wormholes plausible. The real shocker, some solutions in string theory naturally produce traversable wormholes without unphysical energy requirements. These models rely on entangled quantum states, where particles linked across spacetime create a bridge stable enough to traverse. It's as if the vacuum itself stitches together regions of the universe through quantum threads we're only beginning to understand. Of course, the hurdles remain astronomical. Negative energy densities often come with instabilities like a house of cards that collapses if you breathe wrong. And there's the pesky causality problem. Wormholes could, in theory, allow time travel, creating paradoxes that make physicists shudder. But the mere possibility that the vacuum's imaginary energy could rewrite the rules of connectivity in the cosmos is a testament to how deeply the quantum underworld influences reality, or might one day let us bend it. Black holes aren't just cosmic vacuum cleaners, they're the universe's most enigmatic information processors, and their secrets might be written in the quantum vacuum itself. In the 1970s, Jacob Bekenstein and Stephen Hawking made a startling prediction. Black holes have entropy, a measure of hidden information proportional to their surface area. This flew in the face of classical physics, where entropy always scales with volume. How could a three-dimensional object store its secrets on a two-dimensional boundary? The answer might lie in the holographic vacuum, where every bit of information swallowed by a black hole gets etched onto its event horizon like data on a cosmic hard drive. Picture a black hole's surface as a mosaic of microscopic tiles, each tile representing a fundamental unit of space, a Planck-sized patch where vacuum fluctuations churn madly. According to the holographic principle, the entropy of everything inside the black hole gets compressed onto these tiles, encoded in their quantum states. It's as if the three-dimensional interior is projected onto a two-dimensional screen, with the vacuum acting as the projector. This isn't just theory. Hawking's calculations showed that black holes emit radiation, their infamous glow, precisely because of quantum jitters at the horizon, where virtual particles steal energy from the vacuum and escape as real heat. But here's where it gets even stranger. If the vacuum can store information holographically at a black hole's edge, could the entire universe work the same way? Some physicists argue that spacetime itself might be an emergent illusion, woven from entangled quantum bits in the vacuum. Imagine reality as a pixelated image up close. You'd see individual dots of information, but from afar, they blend into the smooth continuum of space and time we experience. In this view, gravity isn't a fundamental force but a side effect of how vacuum entanglement links these pixels together. Debate rages over how literal this holography might be. String theorists point to AD-S/CFT duality, a mathematical framework where a higher dimensional universe with gravity can be perfectly described by a lower dimensional quantum field theory without gravity, like a cosmic cheat code. Skeptics counter that this duality, while elegant, might just be a clever mathematical trick with no physical reality, yet tantalizing clues persist. Black hole entropy formulas align eerily with quantum entanglement entropy, suggesting a deep link between information, gravity, and the vacuum's structure. Perhaps the most radical implication: if spacetime emerges from vacuum entanglement, then black holes aren't exceptions. They're magnifying glasses revealing reality's true, pixelated nature. Every time a black hole swallows a star, it might not be destroying information but translating it into a new language, one where the vacuum's fluctuations hold the dictionary. The next time you look up at the night sky, remember, what seems like empty space might just be the universe's most sophisticated storage device, quietly encoding the cosmos in its quantum whispers. Gravity is the universe's ultimate architect, shaping galaxies, bending light, and sculpting the cosmos. Yet when we peer into the quantum realm, it vanishes like a ghost. For decades, physicists have struggled to reconcile gravity's cosmic dominance with its absence in the subatomic world. But the answer might not lie in some exotic particle or undiscovered dimension. It might be hiding in plain sight, woven into the quantum vacuum's restless energy. At the heart of this puzzle is the graviton, the hypothetical quantum of gravity. Just as photons carry the electromagnetic force, gravitons should, in theory, transmit gravitational waves. But unlike photons, gravitons have never been detected. Why? Because gravity's influence is unimaginably weak at quantum scales. The gravitational pull between two electrons is about 42 orders of magnitude fainter than their electromagnetic repulsion. To spot a graviton, you'd need a detector so massive and sensitive it borders on science fiction. This is where the vacuum offers a backdoor. According to quantum field theory, gravitons, if they exist, should emerge from vacuum fluctuations just like virtual particles. But here's the twist: these fluctuations wouldn't just produce individual gravitons. They'd create a frothing sea of spacetime quanta, tiny packets of geometry bubbling in and out of existence. Picture the vacuum not as empty space, but as a dynamic mesh where every node is a microscopic knot of spacetime itself, constantly vibrating. LIGO, the Laser Interferometer Gravitational Wave Observatory, has already glimpsed gravity's quantum whispers. When black holes collide, their gravitational waves ripple through spacetime, stretching and squeezing LIGO laser beams by fractions of an atom's width. But buried in LIGO data is a faint hiss, the detector's ultimate noise floor. Some theorists argue this isn't just technical static. It could be the jitter of spacetime quanta, the vacuum's granularity imposing a fundamental limit on how precisely we can measure. Efforts to probe deeper are pushing the boundaries of ingenuity. Tabletop experiments using supercooled quantum oscillators or levitated nanospheres aim to detect gravitational forces at microscopic scales. These setups exploit the vacuum's sensitivity. By isolating systems from thermal noise, they become so precise that even the faintest gravitational tug from a nearby mass could reveal spacetime's quantum texture. Other approaches, like holographic noise detectors, search for flickers in laser beams that might betray pixelation in the fabric of reality itself. The implications are staggering. If vacuum fluctuations do hold the key to quantum gravity, they might explain why spacetime seems smooth at large scales but churns like a stormy sea at the Planck length. Some theories suggest that what we perceive as gravity could be an emergent phenomenon, a statistical side effect of countless vacuum-level interactions, much like temperature emerges from the chaos of molecular motion. Yet for all the excitement, the vacuum guards its secrets fiercely. Gravitons, if they're real, might be forever beyond our direct reach, their signals drowned in the quantum noise. But even failure would teach us something profound: that the universe's deepest truths aren't just hidden in particles or forces, but in the silent hum of empty space itself, where gravity and quantum mechanics whisper in a language we're only beginning to decode. Our universe might be just one bubble in an endless cosmic froth, a single pocket of space floating in a vast ocean of other realities, each with its own rules of physics. This mind-bending idea stems from a concept called the false vacuum, where the energy state we consider empty space isn't the lowest possible. it's just a temporary plateau on a much steeper slope. Picture a ball resting on a ledge halfway down a mountain. It seems stable, but one nudge could send it tumbling into the valley below. In cosmic terms, that valley might represent an entirely new vacuum state, one where the laws of physics as we know them cease to apply. Theories like eternal inflation suggest our universe isn't special. It could be one of countless bubbles constantly nucleating in an ever-expanding multiverse, each with its own unique vacuum energy. Here's how it might work. Imagine space itself is a boiling pot of water. Every now and then, a bubble forms a region where the quantum fields randomly fall into a lower energy state. That bubble expands at nearly light speed, carving out a new universe with its own distinct properties. Some of these universes might have stronger gravity, others might have no electromagnetism, and some could collapse instantly under their own unstable physics. We just happen to live in one where the numbers lined up perfectly for atoms, stars, and life. But what if our bubble isn't alone? If another bubble universe collided with ours, the boundary between them would be a wall of redefined physics, a cosmic shockwave rewriting reality as it passed. Some scientists speculate that oddities in the cosmic microwave background, like the infamous cold spot, could be scars from such collisions. Others argue that even if neighboring bubbles exist, they're likely so distant that light from them hasn't reached us yet, and never will, thanks to the accelerating expansion of space. The most unsettling possibility, if our vacuum is truly unstable, a single quantum fluctuation could trigger our own bubble's collapse. The universe wouldn't end with a bang or a whimper, but with a silent, unstoppable wave, a new vacuum state spreading at light speed, erasing everything it touches. The strange part, it might already be happening somewhere out there. A single point in space could have already tipped over the edge, and we wouldn't know until the wall of nothingness was already upon us. Yet for all its existential dread, the false vacuum hypothesis offers a tantalizing glimpse into the multiverse. If true, it means the cosmos is far stranger and more abundant than we ever imagined. A foam of realities, each with its own version of existence, all simmering in the quantum depths. And somewhere out there, in the infinite froth, another bubble might hold the answer to why our universe is the way it is, or reveal that we're just one accidental experiment in an endless sea of possibilities. The universe has a bias, one so subtle that without it, none of us would exist. Look around and you'll notice something peculiar. Everything you see, from stars to smartphones, is made of matter. But according to the laws of physics, the Big Bang should have created equal amounts of matter and antimatter, leaving them to annihilate each other in a blinding flash of pure energy. So why is there anything left at all? The answer might lie in the quantum vacuum's hidden asymmetry, a tiny but crucial preference for matter over antimatter, encoded in the fabric of empty space itself. This imbalance is called CP violation, and it's one of the most baffling clues in modern physics. CP stands for charge parity, a symmetry that, if perfectly upheld, would mean particles and their antimatter opposites behave identically when their charges are flipped and their spatial orientations mirrored. But in 1964, scientists studying neutral kaons, exotic particles that oscillate between matter and antimatter states, found something shocking. These particles decayed slightly differently than their antimatter counterparts, proving nature doesn't always play fair. The vacuum, it seems, has a handedness, like a cosmic scale tipping ever so slightly in matter's favor. Enter Andrei Sakharov, the physicist who laid out the three conditions needed to explain our matter-dominated universe. First, there must be processes that violate baryon number, allowing matter to be created or destroyed. Second, CP violation must exist to break the symmetry between matter and antimatter. And third, these processes had to occur out of thermal equilibrium, a state where the universe wasn't perfectly uniform, giving matter a fleeting chance to outnumber its counterpart. The quantum vacuum checks all these boxes. During the universe's infancy, as it cooled from a superheated plasma, the vacuum's energy fluctuations could have triggered phase transitions, cosmic earthquakes where spacetime itself shuddered, briefly tilting the scales toward matter. Neutrinos, those ghostly particles that barely interact with matter, might hold the key to confirming this. Experiments like T2K in Japan and NRV in the US are hunting for neutrino CP violation by firing beams of these particles hundreds of miles through the Earth, watching as they oscillate between types. If neutrinos and antineutrinos behave differently, it would strengthen the case that the vacuum's chirality isn't just a fluke, it's a fundamental feature woven into the universe's blueprint. The stakes couldn't be higher. If CP violation were slightly stronger, stars and galaxies might never have formed. If it were weaker, annihilation would have left nothing but a sea of radiation. Somehow, the vacuum struck a Goldilocks balance, just enough asymmetry to leave a residue of matter, but not so much that it destabilized the cosmos. So the next time you marvel at the night sky, remember, the fact that you're here to see it at all might come down to the quantum vacuum's quiet favoritism, a cosmic dice roll frozen into the void, tipping the scales ever so gently in our favor. The quietest room in the universe isn't silent at all. It crackles with the quantum vacuum's restless energy, a constant murmur that sets the ultimate limit on how precisely we can measure anything. Consider the atomic clock, humanity's most accurate timekeeper, accurate to within 1 second over billions of years. Even here, vacuum fluctuations introduce tiny jitters, like static on a radio broadcast from the edge of reality. These clocks work by counting the vibrations of atoms, cesium or strontium electrons hopping between energy levels. But the vacuum isn't empty. It's a storm of virtual particles that subtly nudge those electrons, blurring the very ticks we rely on to define the second. This quantum noise isn't just a theoretical nuisance, it's a tangible barrier. Gravitational wave detectors like LIGO, which listen for ripples in spacetime from colliding black holes, must distinguish vibrations smaller than a proton's width from the vacuum's ceaseless background hum. The same fluctuations that spawn virtual particles also create a fundamental fuzziness in every measurement, a limit baked into the fabric of reality itself by Heisenberg's uncertainty principle. You can't measure anything with perfect precision because the vacuum won't sit still long enough to let you, but physicists are fighting back with a clever workaround: squeezed light. Imagine trying to measure a butterfly's wing beats in a hurricane. Instead of battling the storm, you'd reshape your tools to ignore the chaos. That's what squeezing does. It manipulates quantum noise, redistributing uncertainty from one variable like timing to another like intensity where it matters less. By squeezing photons in laser beams, scientists can suppress noise in atomic clocks by half, pushing their precision beyond what was once thought possible. The result, clocks so accurate they drift by less than a second over the age of the universe. The implications ripple far beyond timekeeping. Quantum sensors, devices that measure magnetic fields, gravity, or even the faintest accelerations, are now harnessing vacuum squeezing to peer deeper into nature's secrets. Medical scanners could one day detect neuron firings with unprecedented clarity, while mineral explorers might pinpoint underground deposits by sensing minuscule gravity variations. Even dark matter hunters are joining the fray, tuning their detectors to hear whispers of exotic particles amid the vacuum's roar. Yet for all our ingenuity, the vacuum's noise remains a frontier. Some theories suggest that at even finer scales, spacetime itself might be granular, like static on an old TV screen, a pixelated foundation that no amount of squeezing can smooth away. Whether obstacle or opportunity, one thing's clear: the universe's silence was never empty. It's a canvas of chaos and potential, challenging us to listen closer, think deeper, and measure not just what's there, but what's possible when we dance with the void. You might think empty space is cold. After all, the cosmic void between stars hovers just a few degrees above absolute zero. but delve into the quantum vacuum and the very concept of temperature gets turned inside out. Is the vacuum truly frigid, or does it seethe with hidden heat? The answer depends on who or what is asking. Take an astronaut floating motionless in deep space. Their thermometer would register near perfect cold, the faint whisper of the cosmic microwave background radiation, the only warmth for light years. But now imagine that same astronaut suddenly accelerates. In an instant, their instruments detect something impossible. A warm glow of particles emerging from the darkness. This is the unravel effect in action, where motion through the vacuum transforms nothingness into a thermal bath. From the astronaut's perspective, the vacuum isn't cold at all. It's a roiling sea of particles with a temperature directly tied to their acceleration. The faster they go, the hotter empty space appears. Now switch viewpoints to a black hole's edge. Here, Hawking radiation reveals another twist. The vacuum near the event horizon isn't zero temperature either. Gravitational forces so extreme they warp spacetime itself, tease virtual particles apart, converting them into real heat. To an outside observer, the black hole isn't just cold, it's glowing, radiating energy as if the vacuum itself were a furnace. So which is it, absolute zero or a hidden inferno? The paradox dissolves when we realize temperature isn't an intrinsic property of the vacuum. It's a relationship, a dance between an observer's state and the quantum fields around them. The third law of thermodynamics states that absolute zero can never be reached, as perfect stillness would freeze quantum fluctuations. The vacuum embodies this law perfectly. Its temperature isn't fixed but emerges from interaction, whether through motion, gravity, or measurement. Even in the quietest lab on Earth, shielded from all external heat, the vacuum's zero-point energy ensures it never truly settles to absolute zero. Those tiny fluctuations that jostle atomic clocks, they're the vacuum's way of reminding us true cold is an illusion. Emptiness, it seems, is always restless, a cosmic chameleon shifting its appearance based on how we dare to look. Protons are the universe's ultimate survivors, stable, unchanging, the bedrock of matter, or so we thought. Hidden in the quantum vacuum's depths might lie a ticking clock for every proton in existence, a silent countdown woven into the fabric of reality itself. According to grand unified theories, or GUT, which attempt to merge the fundamental forces, protons shouldn't live forever. They should decay, crumbling into lighter particles over unimaginable eons. But here's the twist: that decay might not be a solo act. The quantum vacuum could play the role of silent saboteur, its fluctuations nudging protons toward their demise. Enter Super Kamiokande, a detector buried a kilometer underground in Japan, filled with 50,000 tons of ultra-pure water. Since the 1990s, it's been watching, waiting for a single proton in its vast tank to blink out of existence, a telltale flash of light betraying its decay. So far, nothing, not a single confirmed proton death. That null result has forced physicists to rethink. If protons decay, their lifetime must be at least 10 to the power of 34 years, longer than the current age of the universe by a factor of a trillion. Why does the vacuum's role matter here? Because in many JUTs, proton decay isn't just a random event. It's tied to vacuum transitions, quantum leaps where the universe's underlying fields shift to a lower energy state. Picture a frozen lake. The ice seems solid, but beneath, water molecules jostle. Given enough time, a rare fluctuation could crack the entire sheet. Similarly, a vacuum transition might destabilize protons, rewriting the rules of nuclear physics in an instant. Some theories suggest these transitions could be triggered by magnetic monopoles, hypothetical particles that are like solitary north poles without south poles. If they exist, they'd act as cosmic catalysts, tunneling through the vacuum's energy barrier and kickstarting proton decay in their wake. Others propose that vacuum fluctuations themselves, given enough time, could spontaneously breach that barrier. The longer we go without detecting proton decay, the higher that energy barrier must be, hinting that the vacuum might be far more stable than we'd guessed. Yet the hunt isn't over. Upgraded detectors like hyper-camiok and with 10 times the sensitivity could push the limits even further. And if protons do decay, it wouldn't just confirm GUTs, it would reveal the vacuum's hidden volatility, proving that even the most permanent-seeming particles are just temporary guests in a universe where nothing lasts forever. Until then, every proton's persistence is a quiet challenge to our boldest theories, a whisper from the void asking, are we missing something deeper? Absorber theory starts with a question so counterintuitive it feels like physics fiction. What if every particle's path through spacetime isn't just determined by the past, but by the future too? In the 1940s, John Wheeler and Richard Feynman proposed a radical idea. The vacuum might not just be a passive backdrop for particles, but an active participant with a kind of memory, mediating interactions through waves that ripple both forward and backward in time. At its core, their absorber theory reimagines electromagnetic radiation. Normally, we think of an electron emitting a photon that travels outward, influencing other particles it encounters. But Wheeler and Feynman flipped this view upside down. They suggested that for every photon emitted, there must be an equal and opposite absorber, a distant particle ready to receive that photon in the future. The catch, the absorber's existence somehow influences the emitter's behavior retroactively, as if the vacuum itself stitches together cause and effect across time. Picture throwing a ball into a room filled with meticulously placed trampolines. The ball's path isn't just about your throw, it's shaped by where the trampolines are positioned to catch and return it. This bizarre symmetry between past and future relies on advanced wave solutions to Maxwell's equations that travel backward in time. While retarded waves, the ones we're familiar with, move forward from an emitter, advanced waves ripple backward from an absorber. In Wheeler and Feynman's vision, the vacuum balances both, creating a cosmic feedback loop where every emission depends on future absorption. The implications are staggering. The entire universe's particle interactions could be a vast, self-consistent network, with the vacuum acting as the medium that enforces this harmony. Decades later, transactional quantum mechanics took this idea even further. Physicist John Cramer proposed that quantum events aren't resolved until a handshake occurs between past and future, a transaction mediated by retarded and advanced waves. In this view, the vacuum isn't just empty space, it's a dynamic ledger where potentialities become real only when the books balance across time. This could explain quantum weirdness like the double-slit experiment, where particles seem to know whether they're being observed. The vacuum's memory of future constraints might subtly guide particles' behavior in the present, but how could the vacuum remember anything? One clue lies in entanglement. Just as entangled particles share instant correlations, the absorber theory suggests all particles might be subtly linked through the vacuum's fabric, their histories and destinies interwoven in ways we're only beginning to grasp. It's as if spacetime has a hidden layer of bookkeeping, ensuring every emission finds its absorber, every cause meets its effect, even if that effect hasn't technically happened yet. Skeptics argue this smacks of retrocausality, a violation of our intuitive arrow of time. Yet experiments in quantum optics have observed behavior that eerily resembles absorber-like effects. Delayed choice experiments, where decisions made after a particle's emission alter its past behavior, hint that the vacuum's accounting might indeed span past and future. Meanwhile, theorists continue to explore whether advanced waves could resolve paradoxes in black hole physics or the nature of dark energy. Whether the vacuum truly has a memory remains one of physics' most poetic mysteries. But if Wheeler and Feynman were even partially right, then emptiness isn't just the absence of things, it's the universe's silent accountant, balancing the books of reality across all of time. The universe tends to repeat itself. From the branching veins of a leaf to the sprawling arms of a galaxy, patterns echo across scales. But what if this self-similarity runs deeper than we ever imagined, woven into the quantum vacuum itself? Some physicists propose that vacuum fluctuations aren't just random noise. They might follow fractal geometry, a hidden order where turbulence at the smallest scales mirrors the structure of the cosmos. This isn't just poetic symmetry. It could be the key to bridging quantum mechanics and gravity, two realms of physics stubbornly resistant to unification. Fractals are infinitely complex patterns that repeat at every magnification, like a coastline that looks jagged whether you're viewing it from space or through a magnifying glass. Apply this to the vacuum and something extraordinary emerges. At Planck scales, where spacetime churns like a stormy sea, fluctuations might not be chaotic but organized in fractal tiers. Zoom in and you'd see the same whirls and eddies repeating, from the tiniest quantum foam to the vast cosmic web. This isn't just speculation. Certain quantum gravity models, like loop quantum cosmology, hint that spacetime's underlying structure could be fractal, with vacuum energy distributed in self-similar clusters rather than smooth gradients. The implications ripple outward. If the vacuum is fractal, it might explain why gravity, the dominant force at galactic scales, vanishes in the quantum realm. Just as a coastline's length depends on how finely you measure it, gravity's strength could scale with the fractal dimension of spacetime itself. Some theories even suggest that black holes, those cosmic singularities where gravity runs wild, might be fractal knots in the vacuum's fabric, their event horizons echoing the same patterns seen in quantum entanglement networks. Evidence is indirect but tantalizing. Studies of cosmic microwave background radiation reveal faint anomalies, patchy distributions of temperature that don't quite fit standard inflation models. Could these be fingerprints of a fractal vacuum imprinted on the early universe? Meanwhile, lab experiments with ultra-cold quantum gases have observed fractal-like behavior in energy distributions, hinting that nature might favor self-similarity even in the quantum regime. Skeptics argue that fractals are just mathematical tools, not physical reality. Yet if the vacuum truly operates this way, it would rewrite our understanding of emptiness. Instead of a featureless void, we'd live in a layered hologram where every fluctuation, no matter how small, carries the blueprint of the whole. The universe wouldn't just contain fractals, it might be one, a vast, whispering recursion where the infinite and the infinitesimal are forever intertwined. In the vast emptiness between planets, where sunlight is just a faint glimmer and gravity's pull is nearly imperceptible, something strange happened to two tiny spacecraft. NASA Pioneer 10 and 11, launched in the 1970s to explore the outer solar system, began slowing down in ways no one could explain. This odd deceleration, dubbed the Pioneer anomaly, defied predictions by a hair's breadth, just a fraction of a nanometer per second squared. But in the precision of orbital mechanics, even the tiniest discrepancy demands an answer. And for decades, the quantum vacuum lingered as a tantalizing suspect. At first glance, the anomaly seemed like a simple case of unbalanced heat. The probes were powered by radioactive decay, their plutonium-filled reactors radiating warmth unevenly across their surfaces. Could photons bouncing off the spacecraft's body exert enough pressure to cause the slowdown? Initial calculations suggested maybe, but not enough to fully account for the effect. That's when wilder theories emerged. Some physicists wondered if the vacuum itself was pushing back, an unseen resistance akin to sailing through molasses. The idea wasn't entirely baseless. Quantum fluctuations exert real forces, as the Casimir effect proves. Could an as yet unknown vacuum interaction be subtly breaking distant spacecraft? Then there were the fringe hypotheses, ideas that flirted with rewriting physics itself. Modified gravity theories like MUND suggested our understanding of inertia might be flawed at extremely low accelerations. Others speculated about hidden dimensions or even a local variation in the gravitational constant. But as data trickled in from other missions like Cassini and New Horizons, no similar anomaly appeared. The vacuum's case grew weaker. By 2012, a painstaking analysis of decades-old telemetry data seemed to settle the debate. Heat radiation, meticulously mapped across Pioneer's asymmetrical design, could explain most, if not all, of the drift. Case closed, or so it seemed, yet whispers of doubt remain. The heat model, while persuasive, still leaves a sliver of uncertainty. And if the vacuum were involved, how would we know? Some researchers propose that future ultra-precise missions, equipped with accelerometers sensitive enough to detect vacuum-level forces, might finally put the question to rest. Until then, the Pioneer anomaly serves as a humbling reminder, even in the void of space, where Newton's laws should reign supreme, the quantum vacuum might still have a few mysteries left to unravel. Gravity has always been the odd one out, a force so weak compared to electromagnetism that a simple fridge magnet can defy Earth's entire pull. Yet its reach is infinite, shaping galaxies and bending the cosmos. What if this contradiction hints at something deeper? Some physicists speculate that gravity's peculiar nature might be because it's not acting alone, that hidden within the quantum vacuum, a mysterious fifth force could be lurking, tweaking gravity's behavior in ways we're only beginning to suspect. Enter chameleon fields, hypothetical particles or energy fields that change their properties based on their surroundings, like a cosmic shape-shifter. Unlike gravity, which weakens with distance but never vanishes, these fields would hide in dense environments like Earth's atmosphere, making them nearly undetectable. But in the vast emptiness of space where matter is sparse, they'd emerge, subtly altering how gravity operates. The idea isn't as wild as it sounds. Modified gravity theories, like those trying to explain dark energy, often rely on similar mechanisms, vacuum-coupled forces that kick in only when the density of matter drops below a certain point. This isn't just mathematical fantasy. Experiments like CASPER, the Cosmic Action Spin Precession Experiment, are hunting for these ultralight, vacuum-linked particles right now. Using supercooled magnetic resonance techniques, CASPER scans for faint whispers of exotic fields that might interact with atomic spins. If detected, these particles could explain not just gravity's quirks, but also dark energy's repulsive push. Imagine a universe where the vacuum isn't just empty space but a dynamic medium, threaded with invisible fields that nudge gravity one way or another depending on where you look. Critics argue that adding a fifth force feels like inventing new physics to patch over gaps in our understanding. But proponents counter that history favors the bold. After all, the neutrino was once just a desperate fix for missing energy in radioactive decay, and now it's a cornerstone of particle physics. Whether chameleon fields or action-like particles are real remains uncertain, but the search itself is revealing. Every null result narrows the possibilities, forcing us to refine our models of how the vacuum truly behaves. So while gravity might seem like the loneliest force, it might just have a silent partner, one that's been hiding in the quantum shadows all along. What if the quantum vacuum doesn't just shape the cosmos, but also the very fabric of consciousness itself? This isn't mainstream physics. It's a radical hypothesis straddling the line between neuroscience and quantum mystery, one that dares to ask whether the vacuum's ceaseless fluctuations might play a role in the emergence of thought. At the heart of this idea lies the ORCH, or theory, proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff. They suggest that consciousness isn't just a byproduct of neural activity, but a quantum process orchestrated by tiny structures inside brain cells called microtubules, and the vacuum might be the silent conductor. Microtubules are the skeletal scaffolding of neurons, hollow tubes made of proteins that help maintain cell structure. But Penrose and Hameroff propose they're far more than cellular scaffolding. These structures could act as quantum processors, their tightly packed molecules vibrating in sync with the quantum vacuum's fluctuations. Imagine trillions of microscopic tuning forks resonating with the hum of empty space itself. According to Orch, or when these vibrations reach a critical threshold, a quantum superposition collapsing into a definite state, they generate moments of conscious experience. It's as if every thought, every flicker of awareness emerges from a dance between biology and the void. The theory's most contentious twist, it invokes gravity-induced wave function collapse. Penrose argues that spacetime itself becomes unstable when quantum superpositions grow too large, forcing them to collapse. This instability, he claims, isn't random noise, it's a bridge between quantum physics and consciousness, with the vacuum's energy fluctuations serving as the medium. Hameroff takes it further, suggesting anesthetic gases might work by dampening these quantum vibrations in microtubules, silencing the vacuum's whisper in the brain. Skeptics, unsurprisingly, have sharp critiques. Critics argue the brain is too warm and noisy for delicate quantum coherence. Decoherence, the tendency of quantum states to unravel in chaotic environments, would destroy any fragile superposition long before it could influence cognition. Yet some experiments hint at unexpected quantum effects in biology. Photosynthesis, for instance, relies on quantum coherence to optimize energy transfer in plants. Could evolution have found a way to harness quantum phenomena in neurons too? The implications, if true, are staggering. It would mean the vacuum isn't just the backdrop of reality, it's interwoven with subjective experience. Consciousness might not be locked inside our skulls, but a phenomenon stretching into the quantum fabric of spacetime. Some even speculate this could explain near-death experiences or the binding problem, how the brain unites disparate sensory inputs into a unified perception. Of course, Orch remains far from proven. Mainstream neuroscience still favors classical explanations where consciousness emerges from complex neural networks, not quantum vibrations. But the theory's boldness forces us to reconsider the boundaries of physics and mind. If the vacuum's fluctuations can nudge particles into being, why not thoughts? Whether fantasy or future revelation, one thing's clear: the quietest corners of reality might hold the loudest secrets. The cosmos might be hiding echoes of its birth in the quantum vacuum itself, a faint imprint left over from when reality was just a trillionth of a second old. If we listen closely, buried in the vacuum's restless fluctuations could be whispers from the inflationary epoch, that brief but explosive moment when the universe expanded faster than light itself. One of the strongest hints, primordial gravitational waves, ripples in spacetime dating back to inflation, that may have etched their signature into the vacuum's structure like cosmic graffiti. The search for these echoes reached a fever pitch in 2014 when the BICEP 2 telescope at the South Pole announced a bombshell discovery. Their data seemed to show a telltale swirling pattern in the cosmic microwave background, or CMB, the afterglow of the Big Bang. This pattern, called B-mode polarization, could have been caused by gravitational waves stretching spacetime during inflation, leaving a faint but detectable curl in the light. For a brief moment, it looked like we'd glimpsed the vacuum's oldest memory. Then came the letdown. Further analysis revealed that interstellar dust in our own galaxy had muddied the signal. The discovery evaporated, but the hunt only intensified. Planck, the European Space Agency's CMB mapping mission, later set stricter limits on these primordial waves. Its data suggested that if inflationary gravitational waves exist, they're weaker than BICEP 2 initial readings implied. But that doesn't mean the vacuum is silent. Future missions like the Simons Observatory and Lightbird are designed to peer deeper into the CMB's polarization, filtering out dust with unprecedented precision. They won't just be looking for waves, they'll be scanning for subtler vacuum imprints, like how inflation's quantum jitters might have amplified certain fluctuations while suppressing others. The real prize, a detection, would confirm that the vacuum isn't just a passive void but an active relic, preserving details from the universe's first moments. Imagine stumbling upon a recording of the Big Bang's aftermath, not in light or sound, but in the way empty space itself vibrates. Some theories even suggest these primordial waves could have seeded the vacuum structure, setting the stage for galaxy clusters and cosmic voids to form billions of years later. But the vacuum doesn't give up its secrets easily. If inflation happened at lower energies than some models predict, its gravitational wave signature might be too faint for any telescope to catch. Alternatively, the echoes might be scrambled by later cosmic events like reheating, when the universe's energy reignited into the hot plasma of the early cosmos. Yet even a null result would be revealing. It would force us to rethink inflation's mechanics, perhaps pointing toward more exotic theories where the vacuum's role is even stranger. Whether we find these echoes or not, the search itself reshapes our understanding of nothingness. The quantum vacuum isn't just empty space, it's a time capsule, a medium that might still resonate with the universe's first heartbeat. And with every new experiment, we're one step closer to tuning in. Every story has an ending, but for the universe, the final chapter might not be as straightforward as we think. Picture a cosmic clock winding down, ticking toward a state where every star has burned out, every black hole has evaporated, and the vast expanse of space stretches into infinite darkness. This is heat death, the ultimate triumph of entropy, where the vacuum's energy is so diluted that nothing can extract work from it ever again. The universe becomes a featureless void, colder than absolute zero in any practical sense, with particles scattered so thinly that they might as well not exist. It's a bleak vision, one where time itself loses meaning because nothing changes anymore. But what if the vacuum has other plans? Some theories suggest that even in this frozen wasteland, quantum fluctuations could spark a rebirth. Imagine the vacuum as an infinite game of chance given enough time. A random fluctuation could, against all odds, assemble atoms into a new configuration. Not just any configuration, but one identical to the universe's starting conditions. A new Big Bang emerging from pure chaos. It's like shuffling a deck of cards forever. Eventually, they'll return to their original order. The catch: you'd need to wait longer than the current age of the universe multiplied by itself countless times. For all practical purposes, heat death still reigns. Yet there's another twist: cyclic cosmology, where the vacuum isn't a graveyard but a phoenix. In these models, the universe doesn't end with a whimper but resets in a fiery bounce. Picture the cosmos as an accordion, expanding until dark energy's grip weakens, then collapsing back under gravity's pull. Each crunch births a new expansion, a fresh universe with slightly tweaked physics. Some versions of this idea rely on vacuum decay, the false vacuum we inhabit tunneling into a lower energy state, releasing enough energy to reboot reality. Others invoke higher dimensional brains colliding in a bulk space, their impacts igniting new cosmic cycles. The most tantalizing possibility: our universe's vacuum might be poised between these fates, its destiny hanging on knife-edge parameters we've yet to measure. If dark energy weakens over time, a big crunch could loom. If it strengthens, galaxies will eventually rip apart in a big rip before heat death finishes the job. And if vacuum instability lurks beneath it all, the slightest quantum nudge could rewrite physics without warning. Perhaps the only certainty is this: the vacuum's fate isn't just a question for physicists, it's a mirror held up to time itself, asking whether existence is a one-act play or an endless encore. The moment you measure a quantum system, something strange happens. Its wavy, uncertain state collapses into a single, definite outcome. But here's the kicker: no one fully agrees on why or how this happens. This is the infamous measurement problem, and it might just have its roots tangled deep in the quantum vacuum's restless energy. At the heart of the puzzle is superposition. the ability of particles to exist in multiple states at once until observed. Schrödinger's cat, both dead and alive, is the classic example, but when you peek inside the box, the cat snaps into one state or the other. The question is, what triggers this collapse? One camp argues it's the act of measurement itself, conscious observers forcing reality to make up its mind. This radical idea, championed by luminaries like John von Neumann and Eugene Wigner, suggests consciousness might be the missing link between the quantum blur and the sharp reality we perceive. If true, the vacuum wouldn't just host particles, it'd be a stage where observation literally sculpts existence. But there's another explanation: decoherence. Here, the vacuum isn't a passive backdrop but an active participant. Imagine tossing a pebble into a still pond. Ripples spread, interacting with the water's surface until the original splash is lost in the chaos. Decoherence works the same way. Quantum systems don't need conscious observers to collapse. Instead, they're constantly buffeted by the vacuum's fluctuations, which destroy delicate superpositions by entangling them with the environment. A single electron might start in a superposition, but trillions of vacuum particles jostling it quickly measure its state without anyone watching. The debate gets even murkier when you consider experiments like the quantum eraser, where seemingly erased information can retroactively change a particle's past behavior. Some interpret this as evidence that consciousness must play a role, that the vacuum's fluctuations alone can't explain such bizarre time-symmetric effects. Others counter that decoherence fully accounts for it, with the vacuum's noise acting as a natural measurement device, far more efficient than any human eye. So where does that leave us? The vacuum might be the ultimate mediator, its ceaseless interactions quietly resolving quantum ambiguities without any conscious intervention. Or it could be a canvas waiting for observation to paint reality into being. Until we crack this enigma, one thing's certain: the quantum vacuum isn't just emptiness. It's the silent referee in the universe's strangest game, deciding when possibilities become facts. From the ghostly flicker of virtual particles to the cosmic whispers of vacuum decay, these 30 mysteries reveal something astonishing. The quantum vacuum isn't just empty space. It's the universe's most vibrant stage, where nothing teems with infinite potential. We've seen how particles burst from darkness like sparks from a void, how black holes evaporate into quantum fog, and how entire universes might lurk in the stillness between atoms. Each paradox the lamb shifts quiet nudges, the unravel affects thermal mirages. Even the terrifying possibility of a vacuum metastability event shows that the line between nothingness and everything is far thinner than we ever imagined. But here's the thrilling part: these mysteries aren't isolated. Tug on one thread and the whole tapestry might unravel. Solve the riddle of dark energy and you might crack the cosmological constant problem. Decipher the holographic vacuum and quantum gravity could fall into place. Even the wildest ideas, wormholes threaded by negative energy, proton decay's countdown, or the vacuum's fractal whispers, aren't just science fiction. They're clues waiting to connect, like pieces of a cosmic puzzle we're only beginning to assemble. So stay curious. The next breakthrough might come from a lab, a telescope, or even a scribbled equation in a notebook. And when it does, it won't just answer one question, it could rewrite our understanding of reality itself. Now, we'd love to hear from you. Which of these vacuum mysteries pulls at your imagination the most? Is it the holographic universe where space-time is a projection? The enigma of dark matter's dance with vacuum energy, or something else entirely? Drop your thoughts below, because the greatest discoveries start with a single shared wonder. And who knows, the next time you gaze at the night sky, remember, the emptiest stretches of space might just be the most alive.